Hi everyone, welcome to the third video lecture in our series on applying machine learning to algorithmic trading. Today I am going to share a powerful secret with you, something I believe is both important and surprisingly unknown in the world of trading. In fact, I searched all over the internet and couldn't find it anywhere. Maybe it is one of those pieces of esoteric knowledge reserved for a select few. But after this video, you will be part of that select group who knows it too. And at the end, I would love for you to tell me whether you think it's truly hidden knowledge and whether you find it useful. Before I can tell you the secret, we first need to talk about the Sharpe ratio. In the previous video, we explored how machine learning predictions can be used to maximize total profit. But I also mentioned that maximizing total profit is probably not what you really want to do, as contradictory as that may sound.
But why not?
Let's take a closer look. Imagine a trading strategy that earns on average 8 basis points per day. A basis point is 1% of a percent. So if you invest $1,000 in this strategy, it will earn 80 cents per day on average. Now imagine another strategy that earns only 4 basis points per day. That's just 40 cents per day for every $1,000 invested. That's half as much. Clearly worse, right? But what if we give to the second strategy $2,000 instead of $1,000 to trade with? Suddenly it also earns 80 cents per day, the same as the first strategy. You might argue that the second strategy is still worse, since it ties up twice as much capital. And to some extent you would be right, capital efficiency is important. But there is another factor that often matters far more: risk. What if the first strategy's 80 cent average daily profit comes with wild swings, say plus minus $10 every day, while the second strategy's profit fluctuates only plus minus $5? Both make the same average daily profit, but the second strategy is clearly more stable and therefore more preferable. Let's illustrate this idea with actual distributions. In the figure, the blue curve shows the distribution of returns for the first strategy. Its average return is 8. Remember, that's 8 basis points per day. The red curve represents the second strategy, with an average return of 4, exactly half as much, assuming both strategies trade with the same $1,000 budget. Notice something important: the red distribution is narrower. That's because the returns of the second strategy fluctuate much less, its standard deviation is smaller. Now suppose we double the trading budget for the second strategy. By doing so, we double its mean return, which is good. However, we also double its standard deviation, which is bad. This adjusted version is shown by the thicker semi-transparent red curve in the figure. And here is the key point: with the doubled budget, the second strategy now has the same average return as the first strategy, but still with less risk, because its distribution is still less spread out, even after the doubling. So in this sense, the second strategy could actually be better: same profit, greater stability. To compare the two strategies, we first scaled the second strategy so that its mean matched the mean of the first strategy. For comparison purposes, we can also scale either strategy up or down so that their standard deviations are equal. For example, if we decrease the budget for the first strategy by a factor of 4, its standard deviation becomes equal to that of the second strategy. The resulting distribution is shown as a thick semi-transparent blue line. With the standard deviation now equal, we can directly compare their means. As shown, the mean of the first strategy after the downscaling is now twice as small as the mean of the second strategy, indicating that it performs twice as bad. A simple and intuitive way to capture this idea is to maximize the ratio of the mean to the standard deviation. This measure is known as the Sharpe ratio. The formula demonstrates how to calculate it. Mu is the mean, and sigma is standard deviation of returns. Alpha is just an arbitrary coefficient. For now you can set it to 1. The intuition behind the Sharpe ratio is that scaling a strategy up or down by changing its budget does not affect the quality of the strategy. Only the relationship between its mean profit and the variability of that profit matters. In other words, a strategy's attractiveness depends on how much return it delivers per unit of risk, not on its absolute size. So how do we build a strategy that maximizes the Sharpe ratio? With machine learning, we could build a model that for any given values of features outputs a probability distribution from which the target, that is the price change, is expected to come. By changing the values of the features, we change the parameters of this distribution, its mean, variance, skewness, kurtosis, and so on. But before we start building a predictive model that outputs the full probability distribution of price changes, we need to know how we are going to use these distributions. We don't want to spend time and effort producing something without a clear purpose. Before we go further, let me introduce a new term, position, also known as allocation. This is how much we need to buy. If this number is negative, we need to buy a negative amount, and it means that we need to sell. So in fact, when it comes to choosing a position, the amount that we need to buy at each step to maximize the Sharpe ratio, we might not even need the full probability distribution. We may only need certain properties of it, and also a formula for combining those properties into the final position size. To illustrate this, let's first recall the problem of maximizing the total profit instead of the Sharpe ratio, something we have already discussed in the previous lecture. Back then, all we needed was the mean/average of the distribution from which the price change is expected to come for the given values of the features. So we did not need anything except the mean. To find the optimal position, optimal in the sense of maximizing total profit, we just looked at the sign of the mean. If the mean was positive, we put our entire budget into buying. If the mean was negative, we used the same amount to sell. That approach would maximize total profit over a long run. But now the question changes. What if our goal is to maximize the Sharpe ratio instead of total profit? More specifically, what properties of the probability distribution do we need to know, and how should we combine them to get the optimal position, optimal in the sense of maximizing Sharpe ratio? Let's frame this question more rigorously and mathematically, and then see what the best LLMs out there have to say. This is how we formulate the question. We are considering a sequential game that unfolds over a series of steps. At each step, we are given a different probability distribution PDF. We know everything about this distribution, its mean, variance, skewness, kurtosis, and any other relevant properties. Using these properties, we must decide on a single number, which we will call our position. We then draw a random number from the distribution, which we will call the change. Our profit for that step is calculated as a product of position and change, so profit equal position multiplied by change. We repeat this process over many steps, each time facing a new and different PDF, and collect our returns. The problem: we want to determine a rule or strategy for choosing our position at each step based on the known parameters of that step's PDF, so that the Sharpe ratio, defined as the mean return divided by the variability or dispersion of returns, is as high as possible over the entire sequence of steps. Please solve the problem and write the formula for the position in the end. So let us look at what Grok 3 says. As we can see, the answer it gave is mu divided by sigma squared, where mu is the mean of the distribution and sigma is standard deviation. And by the way, sigma squared is the variance of the distribution. Now let us look at what Claude Sonnet 4 has to say. It is the same answer, mu or mean divided by sigma squared. Now let us switch to Gemini 2.5 Flash, the same answer. And finally GPT-5, again the same answer. Here is the fun part: this answer, generated by all the LLMs I have tried, is not correct.
But why not?
I'm not entirely sure why. Maybe my question was misleading, though I honestly can't see how. In any case, I'm going to give you the correct answer, and just to be sure, I will prove that it's correct. And now, here is the promised secret. The correct formula for the position that maximizes the Sharpe ratio is mu divided by sum of sigma squared and mu squared. If at each step, say every day, you calculate your position using this formula, you will achieve the best possible Sharpe ratio over the long run. I remind that mu and sigma are the mean and standard deviation, or rather your estimates of them, for the next or future price change. As we can see, having just an estimates of mean is not enough to optimize the Sharpe ratio. I have derived this formula analytically, so I have a strict analytical proof of it. Its derivation is not based on any assumptions or approximations, so it will work in any situation and it gives the precisely correct result. I will not provide this derivation here, as it goes far beyond the scope of this lecture. What I will do, I will demonstrate numerically that it gives better results when compared with the alternative formula given by all the LLMs I have tried. So let us prepare everything for our numerical simulation. First, we need a function that calculates the Sharpe ratio. It is implemented in cell 188. Next, we need a function that returns a single random number from a distribution given by its mean, standard deviation, and shape. It is implemented in cell 189. In our case, we consider just two shapes. The shape argument can have only two values, n and u, standing for normal and uniform distribution respectively. The last simple function that we need for our simulation is implemented in cell 192. It returns a given number of arbitrary probability distributions, or more precisely, it returns not distributions but their parameters, value of mean, value of standard deviation, and a letter specifying the shape of the distribution, with n standing for normal and u standing for uniform. In cell 194, we generate parameters for 10 random distributions and print them one by one. Now, finally, we have everything we need to run our simulation. We organize an experiment as follows. We take an arbitrary number of different arbitrary probability distributions with known means and standard deviations. Then, within a single experiment, we do many steps. On each step, we randomly take one distribution out of the mentioned set of probability distributions. Based on the mean and standard deviation, mu and sigma, of the taken distribution, we calculate two positions. The first position is calculated as mu divided by sigma squared, formula suggested by the LLMs. The second position is calculated using our formula, mu divided by sigma squared plus mu squared. Then we sample a random price change from the selected step-specific distribution and multiply this price change by the two different positions to get the two different returns or profits. This concludes the first step. All the other steps within an experiment are done in exactly the same way. Each step produces a new pair of profits. After that, we calculate Sharpe ratio for both sets of profits. So we get a pair of Sharpe ratios as a result of a single experiment. To run the second experiment, we take another set of arbitrary distributions and run our new experiment exactly the same way as we run the first one. We do many such experiments, and this way we get many pairs of Sharpe ratios. In these pairs, the first Sharpe ratio is what we get when we use the first incorrect formula for the position, and the second Sharpe ratio is what we get when we use our own correct formula. Finally, we visualize our results. As you can see on the figure, the Sharpe ratios obtained with our formula for the optimal positions are always higher than the Sharpe ratios obtained with the alternative formula proposed by LLMs. Okay, now we know that in order to maximize Sharpe ratio of profits, we need to know the mean and the standard deviation or variance of price changes. So we can start thinking about how to estimate these two parameters. One approach might be to build a predictive model that, for any given values of features, outputs the entire probability distribution of future price changes. And yes, that's possible. Machine learning can tell you how to do this. But it's not optimal for our purposes.
But why not?
Here is why. When you train such a model, the optimization process will try to balance accuracy across all aspects of the distribution: mean, variance, skewness, kurtosis, and so on. That means it could end up sacrificing accuracy of the mean or variance, which are the only things we actually care about, just to better capture some other properties like skewness and kurtosis, which we don't need. On top of that, a full distribution model is much more complex and requires more data to train well. And as you will see in upcoming lectures, in finance there is always a lack of data because of high noise-to-signal ratio. So the last thing we want is to waste valuable data predicting properties we don't even use. Instead, we should focus our data and modeling effort entirely on estimating the properties that matter to us, the mean and the variance in our case. So now we can start thinking about how to predict the mean and the variance. Estimating the mean is straightforward. We already learned how to do that in the previous lecture. Just to remind you, you train a machine learning model using relative price changes as targets and minimizing the mean squared error. But what about the standard deviation? How can we predict it? First, note that in the formula we have standard deviation squared, or sigma squared. Square of standard deviation is nothing but variance, and variance can be calculated as mean of squares minus square of mean. Look at the first formula. Now, in the denominator we have square of sigma plus square of mean, so the square of mean cancels out, and the denominator becomes equal to the mean of squared price changes. As a result, our formula for the optimal position gets a very elegant form. In the numerator we have the mean of price changes, and in the denominator we have the mean of squared price changes. To get the mean of the squared price changes as a function of features, we can take our targets, which are relative price changes, square them, and use those squared values as new targets to train the second model. Just like with the first model, if we minimize the mean squared error during the training, the resulting predictions can be interpreted as feature-dependent estimates of the mean of targets. In our case, that means the mean of squared price changes, exactly as we need. So we just built one model for the numerator and another one for the denominator. In other words, we train the first model to predict relative price changes, and we train the second model to predict squared relative price changes. When training both models, we need to minimize mean squared error. This is very important. Then our positions should be calculated as predictions of the first model divided by the predictions of the second model. Positions calculated this way should maximize the Sharpe ratio of returns. With this practical advice, we can conclude the current lecture. If you learned something, please hit the like button. If you have any questions, suggestions, or requests, feel free to leave them in the comments. I will do my best to read and respond to each one. And don't forget to subscribe so you don't miss any new videos. Thank you.